OCR A, A-level physics, medical physics number 3, part 3. And this video is about ultrasonics. So, an ultrasound scan, so high frequency, high intensity sound waves to produce an image. And it can produce real-time images or video of things inside your body. For example, to look at the health of an unborn baby during pregnancy, to get images of internal organs such as the heart and the liver and the kidneys, and also to guide surgery. If you're doing a bit of keyhole surgery and you want to know what you're doing, you might use ultrasound. Okay, so you use a transducer, and the transducer changes an electrical signal into ultrasound waves. The ultrasound goes in the body and some of it will reflect back, and then the same device, the same transducer, picks up these waves and converts them back into an electrical signal. And it's all to do with something called I call it the piezoelectric effect, or the piezoelectric effect, however you pronounce it, the piezoelectric effect. A bit more about this transducer. So you put an alternating voltage across some crystals and they vibrate, yes, at the same frequency. So alternating voltage, they vibrate, they produce ultrasound waves, yes. Then when the vibrations come back, the crystals vibrate and they produce an EMF, they produce a voltage of the same frequency, yes. And that's the piezoelectric effect, and that's what's happening inside the transducer. So we have our piezoelectric crystals in the transducer there, yes, an acoustic lens to focus it, and then the crystals are arranged in a pattern like that. Now, the crystals have a natural frequency. Do you remember when you did simple harmonic motion and resonance, etc.? So the crystals have a natural frequency, and the waves they produce have the biggest amplitude when you use that frequency. You send the waves in pulses so that you're giving it time for the waves to get there and back before you send the next pulse so that it doesn't interfere. You have a backing layer which dampens, there's the backing layer there, and that dampens the vibrations so that it's not vibrating anymore in time for the next pulse to come along. Now, ultrasound is sound which is above the range of human hearing. So anything above about 20 kilohertz is ultrasound, but in these ultrasound scans, they use between 1 megahertz and 5 megahertz, so well above the range of human hearing. And that gives you a resolution, that's the smallest detail that you can see, of about 1 millimeter. Acoustic impedance, okay? Now, impedance, it's a bit like resistance. Electrical resistance is how hard it is for a current to flow through something. Acoustic impedance is how hard it is for ultrasound to flow through something. And the acoustic impedance, capital Z, we see that we work it out. It's the density of the material multiplied by the speed of sound in the material. And here's a table, and if you look, I've got the velocities there, and I've got the densities, and I've got the acoustic impedance. And looking at that, you will notice that air has a very, very, very small acoustic impedance, so lots of ultrasound goes through it. Bone, compared to the others, has a very high acoustic impedance. The others are very similar. Now, when a sound wave meets a boundary between two materials, this is where reflection takes place. When you've got a boundary, so you've got one medium and you've got another medium. And what will happen is that some of the wave will be reflected and some of the wave will be transmitted. And the ratio of the intensity of the wave reflected to the intensity, which is, well, the incident intensity, the intensity coming in, depends on the two acoustic impedances. In fact, it depends on the difference between them. The bigger the difference between the two acoustic impedances, the more of the wave is reflected. And you may need to use this equation here, and that's to calculate. So IR is the reflected intensity, II is the incident intensity, the original intensity. Okay, and as I said, the bigger the difference between them, then the more of the wave is reflected. Now, as the wave travels through the body, it reflects off boundaries between tissues. And then from the data received from the reflected waves, an image can be produced of those boundaries. So what we're looking at is the boundaries between different types of tissue, different media. Okay, now looking at this is important. If you look at the acoustic impedance of air, it's about 400. If you look at the acoustic impedance of skin, it's about 1.7 million. There's a huge difference between them. And that means that at the gap between air and skin, you're going to get massive amounts of reflection. Okay, and that would cause a big error. Okay, you're not going to get very much information from inside the body if you're getting such huge reflections just at the skin. So we use a coupling gel. So you put gel on the front of the transducer, and that goes between the transducer and the skin, and it gets rid of any air so that there aren't any air bubbles in there. Okay, and then the gel has a very, very similar acoustic impedance to the skin, so there's very little reflection at that boundary. So that's why we use a coupling gel, so that there's no air in the gap. If there was air in the gap, you'd get a massive amount of reflection at this boundary between the air and the skin. Okay, now the acoustic impedance of soft tissues is very similar. So if you look at water and muscle and fat, they are all very, very similar. And that means that you're actually going to get very little ultrasound reflected. But you get enough to form an image. Yes? Where bone is involved, at a bone tissue boundary, you get lots of reflection. So ultrasound isn't very good if there's bone in the way, if there's bone involved. At an air soft tissue boundary, for example at the lungs, then nearly all of the ultrasound is reflected. So basically ultrasound is good at looking at the boundaries between soft tissues. So things like for a fetus, for an unborn baby, yes, because the bones haven't fully developed yet. Ultrasound, very, very good. Two types of scan. Now, there's the A scan and the B scan. The A stands for amplitude. B stands for brightness. Yes? Now, the difference between them, the amplitude scan is one-dimensional. So what you're doing is you're sending a pulse in a straight line, and the pulse travels through the body and it reflects off different boundaries. And then looking on the oscilloscope screen, you'll see that's the reflection being detected on the oscilloscope screen. Okay, a one-dimensional scan where all the surfaces that you want to look at are in a straight line. And then an oscilloscope displays the sent pulse and the reflected pulses. And then from the time that it takes for the pulse to get back, you can work out the distance to these boundaries. Okay, this is used, a couple of uses, to look at the eye. If you want to measure the diameter of somebody's eye, and there's some pretty horrible videos on YouTube where they're putting this thing on top of somebody's cornea. Also to monitor the size of the head of a fetus, and that's one way that you know how far into the pregnancy it is, okay, by looking at the size of the head of the fetus. So that's an A scan. Now, the B scan is two-dimensional, and it's a brightness scan. And this produces images of sections, slices through the body. Okay, and basically the signal that you get back, the intensity of the signal that you get back, controls the brightness of this two-dimensional image on the screen. Looking at the animation, hopefully that explains what's going on. Potentiometers monitor the position and the orientation of the transducer. If you watch somebody doing this, they usually just rock the transducer so that they're changing the angle, like on the animation, but they're not really changing the position. Yes, so the beam is rocked, so the beam comes in at different angles, and then all of this information goes to a computer, and it can produce a two-dimensional image of a cross-section through the patient's body. This is, I'm sure you've seen videos on YouTube of ladies having a scan of the unborn baby, and the doctor or the nurse is rocking the transducer over the tummy, like they cover it in gel first, and then they're rocking the transducer, and then looking at the picture, ooh, is it going to be a boy? Whatever. Now, ultrasound can be used to measure the speed of blood flow. And it uses the Doppler effect. You know what the Doppler effect is by now, don't you? Yeah, when we did astrophysics, we talked about the Doppler effect. And so basically what we're doing is we're putting ultrasound waves and they bounce off the red blood cells inside a blood vessel. And then because the red blood cells are moving away from the transducer, there is if you like, a redshift. Although we're talking ultrasound, we're saying that the wavelength is a little bit bigger, and so the frequency will be a little bit smaller. This is very useful for looking at, amongst other things, for looking for blood clots, poorly working valves, for example, in the heart and in the veins. In something like an artery, there isn't a steady flow of blood either. The blood, you know, with the pulse, it goes forward and then maybe a little bit backwards, and then forward and then maybe a little bit backwards. But at any point in time, or as a function of time, we can measure the velocity of the blood as it travels through these blood vessels using an ultrasound Doppler effect. This is the equation that you need to know. So delta F over F, delta F is the change in frequency, F is the original frequency. The speed of ultrasound in soft tissue, you would be given 1570 meters per second. V is the blood velocity. Theta is the angle between the ultrasound pulse and the blood flow. So if you imagine kind of that's the vessel there, and then the ultrasound transducer is there. So we're talking this angle here is theta. Okay, typically it's about between 45 and 60 degrees. And use that equation there to calculate V, and having shown you that, have a go at that and see what answer you get. And the answer is, in 3, 2, 1, about 0.3 meters per second, which is about right for an artery.